Hello, everyone. I welcome you at the Yerevan Mathematical Colloquium. Today's talk is by Levon Nurbekyan from UCLA, who will talk about mean field games. Please.
Thanks a lot, Armen, for invitation. I'll try to talk a little bit about mean field games today. So in the abstract that I submitted for the talk, I think I was overly ambitious and tried to and trying to talk about three things. But today I'll actually present two aspects of mean field games because I'm assuming that the audience has like broad expertise, so they're not particularly experts in mean field games, and so maybe it's going to be better if we do things in a slower pace. Okay, so these are my research interests broadly. So I'm interested in mean field games and also related theory of optimal transportation. Those are all also connected to calculus and variations, optimal control theory, PDEs, and some of applications of these types of problems and theories are in modern topics such as machine learning, the data science, but also game theory, economics, industrial engineering, and so on. So the agenda for today would be to try to introduce the mean field games a little bit, and then I'll talk about two aspects of interest. So one, I'll show you one application in machine learning, and also I'll PD problem that appears. Mean field games in their modern formalism were introduced by two groups. So one in Canada, Min-Yu Huang, Roland Mohamed, Peter Keynes, and they're interested in problems that arise in industrial engineering. So in Canada, they bring the energy or electricity from the northern part of the country where you have lots of waterfalls and etc. And so essentially they're interested in problems where you have large electricity grids, and they're thinking about some problems where the consumers could have devices at their homes so that you could buy or sell electricity to the grid to make the whole process more optimal. So these are types of problems that they were interested in, more in the industrial engineering. And on the other hand, by Jean-Michel Latry and Pierre-Louis Lyons. So Jean-Michel Latry is a mathematical economist, and Pierre-Louis Lyons is a mathematician and applied mathematician. His primary research interests were in partial differential equations. So you can see these two different flavors coming in. So in a nutshell, very quickly, there are a framework of rational agents that play certain kind of games or differential games. And if you're familiar with the classical, let's say, fluid dynamics or statistical physics, then you could think about these mean field games as an analog of equations, that macroscopic equations that come from statistical physics, but instead of the underlying microscopic physical principle where you have, let's say, Newtonian mechanics, for example, you have principles of game theory or optimal control theory. So that's a very high level yeah. Yeah, so there are numerous applications for this field, and it's currently growing, in fact. So there are applications in econ, finance, industrial engineering, swarm robotics, epidemic modeling, data science, and so on. And it's often hard to keep up with the growing literature on Google Scholar. So to introduce the problem of initial gains, we need to look a little bit at optimal control problems, because this is the foundation that the means are based on. So that's why for a couple of slides I'll try to explain a little bit of optimal control theory and the aspects of this theory that are interesting for and relevant for us. So an optimal control problem looks as follows. So we have to minimize the following cost function, and the cost function consists of two parts. One part is this integral from little t to capital T, L, S, ds, us, plus the second part, the function g of dft. So z is the trajectory of our system of interest. So let's say we have a certain system. You can. Was there a question? No. So we can think about any system, for example, in flying airplane or a car or whatever other system, where the state of the system is characterized by some variable z, and if the state of the system is changing in time, then of course we have a curve z s, where s stands for the time variable. And we assume that the state ds satisfies the following differential equation. So z dot equals to f s g u, and the variable u is our control that we're allowed to choose. And we assume that this u is a function, is a time-dependent function, with the image being, for example, about this control. For example, if you're driving a car, so you could incorporate, for example, the angle that you steer your steering wheel with, and it could also be that how much you press the acceleration, and so on. So this could be the controls, and z could be the coordinates or the position of the car. And so if you choose your controls, evidently that the position of the car will change according to some differential equation, which is incorporated in this function f. So little t, we say it's the initial time, capital T is the terminal time, and we also assume that x is our initial position. So t, the coordinate or the state of our system at little time t, equals to x. So L here is called a running cost, or sometimes Lagrangian, because of resemblance to classical mechanics. And G is called a terminal cost. So essentially, you're steering your system according to some control U. You're paying a running cost. So this is an integral from T to T. So in the duration of during your control problem, so time horizon. Plus, when you arrive somewhere and your arrival coordinate is D at capital T, you pay some terminal cost. This is the typical optimal control problem. So there are variations of these problems. There are infinite time horizon problems, and so on. So there are many variations, and also in this case, deterministics and so on. So you could have state constraints and so on. So you can make the problem more and more complicated. But for the purpose of clarity, I'm considering this more or less a simple example. And yeah, please feel free to interrupt and ask questions. Okay, so this is the optimal control problem. Now, how do we solve these types of optimal control problems? So there are two approaches to solve this problem. So one approach is more or less direct approach, which follows the following idea, that if you have infinite dimensions, if you have a minimizer for a function, then you have that minimizer is a critical point, so that the gradient or the variation of your function or function of that point equals to 0. And so this optimal control problem is an example of optimization problem. It's just that we're optimizing over curves. It's an infinite dimensional optimization problem. But nevertheless, it is an optimization problem. There should be first order optimality conditions to be able to solve this problem. And so these first order optimality conditions are known under the name of Pontryagin maximum principle, and they work as follows. So we introduced this calligraphic age, which is called sometimes the Hamiltonian of the system. And again, the names come from the resemblance with the class. So it's a joint variable P, and then it's negative P inner product with S minus L. And so theorem, and of course I'm dropping all of the assumptions here, again for clarity, but under certain assumptions where we would have, let's say that the problem would meet a minimizer and so on and so forth. So under certain regularity assumptions on L, T, and F on the data of our problem, we have the following results. So let's assume that V star U star is a pair of optimal trajectory and control. And let's assume that P, a curve, solves the following adjoint equation. So it's P dot equals to the partial derivative of this calligraphic age with respect to the position variable Z, computed at L V star P U star. And it has a terminal condition, the terminal condition being equal to the gradient of the terminal function at the point where we arrive. Okay, so given V star U star, an optimal pair, then I can, again, under certain regularity conditions, I can solve this ODE with respect to P. It's a terminal condition ODE, so I have to solve it backward in time. So once I do that, it turns out that there is a following relation between V star, U star, and P. So U star S is maximizing the calligraphic Hamiltonian. And that's why it's called a Pontryagin maximum principle. Okay? So if we collect all of these difference for the joint variable, and we add to that the differential expression that the state of the system satisfies, we arrive to the following closed system, right? So we have a differential equation for Z, an OD for the position variable, an OD for the joint variable, a relationship between the optimal control and the trajectory. So there's a typo here. It should be argmax calligraphic age S P star U, so not U star S. And the initial and terminal conditions. Okay, so this is a very typical property of optimal control problems, that you obtain initial terminal conditions. So typically, when we're thinking about some evolution equations like heat equation, wave equation, or other types of equations that are characterizing some natural phenomenon, in those cases, typically, because they're evolution equations, we have initial value problems. So the initial values of our, let's say, system or the unknown are specified, and we want to find it like in all the other times. But control problems, they have a different flavor. They always come with some initial and terminal conditions, and the reason is that we're optimizing our controls, right? So there should be a sort of forward-looking component to terminal. And so one thing that makes these types of problems complicated, for example, to solve is because it becomes a global problem on the whole time horizon, little t capital T. So if you change, capital T, if you change the time horizon, physically speaking, right, the system changes and you have to find a solution from a clean slate. Whereas if you have an evolution equation, you just propagate whatever solution, you stop somewhere and you can propagate again. So that's the difficulty in these types of problems. Okay, so the system looks a little bit complicated, right? But it's often possible to get rid of and to eliminate the control variable and to obtain a system only in original in the state and adjoint variable. And it's done as follows. So we introduce this age now state that does not depend on the control variable, and it's exactly equal to the maximum value of the telegraphic age. Then you can see that the previous system can be rewritten as follows. So it's now a system of ODE with respect to a state variable and adjoint variable. And again, it has its forward-backward structure. And the system is called the Hamiltonian system. Again, it resembles, so if you're familiar with classical mechanics, right, you see that the ODT strategy, the Hamiltonian is from classical mechanics. But again, the key difference is that in mechanics we have an evolution problem. Here it's a control problem. That's why the adjoint variable has a terminal condition which is tied with which is coupled with the terminal condition, the terminal position for the state. Okay, but anyway, there are many things that are similar to this. Okay, so in principle, we could try to solve, and by solve I mean, for example, numerically, right, computationally, we could try to solve this this optimal control problem by solving this system of ODE, or the previous one with which still had the control variable and it wasn't reduced, right? So what are some of the advantages and some of the advantages of the Contradi-Martin principle or the Hamiltonian system? So if we're trying to solve this problem for high-dimensional control problems, and by high-dimensional I mean that the variable lives in a high-dimensional Euclidean space, and similarly the control variable could also live in a high-dimensional Euclidean space, then because we're working on the level of ODEs, we do not need to utilize space grid. So when you discretize the problem, we do not need to discretize the space. We only need to discretize the time, and therefore we can try problems using this technique. Now, one of the main disadvantages of this approach is that it's highly dependent on initial data. Right? So if we solve the problem for some initial data t and x, so from time t and position x. Now, let's say for some reason the initial position and time change. So, for example, we can think about a UAV flying or some other system, and there is a certain wind interference or something like that. So the position or the state of our system changes on flight. Then, if we're at the new position, we have to solve the problem again for this new position. And if our solver is not fast enough to do this in real time, then we'll have a problem there. So this technique, although it's nice from the point of view of not utilizing space speed, but it's challenging because we start from a new position. We have to solve the problem again. So there comes a different strategy to solve this problem that is called the Hamilton-Jacobi-Bellman PDE, and it works as follows. So let's introduce this function phi, which we call a value function, and it depends on initial time and position. So phi tx is just the So it's the value of the infimum. And it turns out that this value function phi satisfies in an appropriate sense under appropriate assumptions on L and V a specific partial differential equation, which is called the Hamilton-Jacobi partial differential equation, that looks as follows. So minus partial T phi plus H, the straight Hamiltonian that I introduced here, and there is a typo here. I forgot to put time variable in the Hamiltonian. Anyway, H, Tx, gradient of phi, and when I write gradient, I always mean the gradient with respect to space variable x equals to 0, and the terminal condition equals to the terminal cost. Okay, so this is an extremely nice thing that if we can solve this partial differential equation, we can find its cost without actually need of solving the control problem directly, right? So this is an interesting property of the value function. It's a backward running problem, and again, this comes from the control flavor. Now, what is even more important and interesting is the following: that this function phi allows you to find the adjoint variable and the optimal control without the need of solving that system of differential equations, so system of ODE. So how does it work? The precise conditions under which this theorem is true, but yeah, so they can be found in the literature. It's not so difficult, and they're sort of standard. So given optimal trajectory V star, the adjoint trajectory, so the flow variable T that I introduced, is simply the gradient of phi, the space gradient of phi. And so if we know phi, we know the flow for the adjoint variable T, and so we can find the optimal control via maximizing this calligraphic H at each point in time. And often, this maximization problem for many systems in practice, this maximization problem could actually be solved analytically. So for fixed T, D, and T, you can find this argmax of U often analytically, given by some function that I denote here by J. And we can obtain the optimal controls as follows. It's a function, an analytic function, or something that is easy to compute numerically, from the time, position, and the gradient of phi. And you see that this means that if I know my current time and position, I know the optimal control. And these types of, if we find the optimal controls in this form, they are called the feedback form. So essentially, you know your time and position, you plug in to the function that depends on your time and position, and you know what to do. You know how to move according to that. You know how to move to mode. So in some sense, it means that the value function phi acts as a master function for a control problem, because it has all of the information that we're interested about in terms of the control problem. So the adjoint variable is going to be the gradient of this master of this function phi. The control can be found using this function phi, and also once we know this function phi, at each position we know how the state of Z will change. So we have all the information about the control problem, and so knowing the value function phi, it's almost equivalent as to knowing the solution or solving the problem at all initial points at once. And so if you have access to phi and its gradient, then you can compute optimal actions rapidly. And it doesn't matter if your position changes on the fly, you still have, you just look at your current position and time, and you have, let's say you have access to the function phi, you can find it in, you can find optimal actions rapidly. And this is extremely important if you're interested in real-time control application, because you don't have time to compute the optimal trajectories. It's nice that you have them in a feedback in a feedback form. Okay, so now once we control optimal control, we can look at mean field gain. So in mean field gain, instead of one agent or trying to solve a optimal control problem, we have a population of agents or players, and each of these players is trying to solve an optimal control problem. Okay, so we have to introduce also the interaction mechanism between one agent and the other one. And the way we introduce this interaction mechanism is as follows. So let's assume that the agents are distributed in a state space according to some probability distribution rho, so I denoted by rho at the time s. Okay, so distribution of agents in state space is this, and you can think about, let's say, you're trying to find your way through a crowd, and you know, when you're trying to find your way through the crowd, you're not really interested in individually every person in this crowd, and you're sort of trying to model the crowd as some sort of a density distribution, right? So this part is a little bit more dense, there are more people, so maybe I want to go this other way, but maybe this other way, you know, the way is too long, so maybe I could compromise to go to the part of the crowd that is not so dense, and also it's not so far from my terminal location. So anyway, every agent models distribution of the whole plate, and the distribution enters as a parameter in your optimal.
Something with the voice?
Problem. So you see here, I highlighted the terminal. Can you hear me well? Can everyone hear me? Or
yes,
anyone
now,
hear me?
Now, yes.
Now, yeah, it went off, but now I think people can hear.
Okay. 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 Great. Okay. Yeah. So, what are the? Okay. So we have this situation where each agent tries to optimize a problem, and they optimize their cost, and they're interacting through the dependence of the running cost and the terminal cost on the distribution of the population. So let's see how can we describe the equilibrium configurations here. So from the perspective of each agent, they're simply solving an optimal control problem. And we're assuming here that each agent is small, so to speak, in a sense that when they are modeling what's going to happen when they choose their actions, they think that these actions will not affect the whole population. Okay, and you can think about, let's say, when you're let's say driving to work in the morning, and you're trying to choose which highway, you're assuming that, let's say, highway number 1 is this much crowded, highway number 2 is that much crowded, and then you're doing your calculations. But in your calculations, you think that, okay, whichever highway you choose, this is not going to change the distribution drastically, and so the population distribution on the background is something fixed when you're solving the problem. And that's why, from the perspective of each agent, they're solving a optimal control problem that, as we discussed, can be described in terms of Hamilton-Jacobi-Bellman PDE, with the only difference now that the Hamiltonian and the terminal cost, they depend on the density of the population. So the optimal controls are still given in a feedback form. And again, the only difference is that the Hamiltonian carries now a dependence on the distribution. So this part is This is almost the same as before. It's just that there's this extra parameter. Now, we also need another condition here, and this comes from the following observation. So every agent in their mind, they're saying, okay, let's say that the distribution is given by this density, and then they start acting optimally according to these optimal controls in the feedback form. Now, when they end up acting and they see that their distribution, that the resulting distribution does not agree with what they had in mind, then you are not at an equilibrium. So if you thought that highway number 1 there's not a huge number 1, and then it turns out to be extremely crowded, right? This is not an equilibrium situation. So next time you make your decision, you have to adjust your belief about the distribution of the population on the background. Okay, so but if you go there and see that, you know, if every agent chooses their highway and they end up and they see that the situation on the highway matches what they thought it would be, then they would every day essentially choose the same route. Everyone would choose the same route, and then you're in an equilibrium configuration. So how is it? How can we write it in this setting of ours? Well, because agents are acting optimally according to these actions, their density evolves according to a partial differential equation, which is called the continuity equation, where you have which is written here. So you see that the optimal actions there enter through this partial derivative of h, and we also assume that the agents are distributed initially according to some known distribution rho naught. So if you collect all of these equations together, at least formally, you get the following system of partial differential equations. Why do I say formally? Because every time you consider a complete system, you have to make sure that you have to make sense. Typically, these equations do not have smooth classical solutions, so you have to make sense of all of this. But formally, we can write them down. It has this typical structure. So you have a Hamilton-Jacobi equation, which is coupled with a continuity equation. So the density has some initial condition, and the value function has some terminal condition. And again, you see that initial terminal condition structure, which is because the problem has some control favor. So what are the advantages of looking at this mean field gains PDE? So you could write equilibrium configuration for finitely many agents. So let's say you have 10,000 agents, 1 million agents, or whatever. You could write the equilibrium conditions for these large agents, and instead of getting this system, you would have a large system of nonlinear partial differential equations. So, and the number of equations would be equal to the number of agents that you have. And it's extremely hard to study this system and also to numerically compute the solutions. And so here, what mean field gains PDE does is as if you go to the continuum limit when the number of agents goes to infinity, and using the symmetry of the agents and using their smallness, essentially all of those differential equations for each agent, they collapse to one equation, which is given by the Hamilton-Jacobi equation, and at the expense of one extra equation, which is the continuity equation on the second one, evolve. Okay, so again, this is very similar to, let's say, Euler's equation in fluid dynamics, where instead of modeling particles one by one using the Newtonian mechanics, you look at statistical bulk quantities or properties of the system. So another advantage that the system has is that it yields near optimal solutions when you apply the controls found here to finite population. So you go to this continuum limit, you solve this problem, and then you apply the controls that you found here to a finite agent case, and you can prove in many instances that you find almost optimal solutions. And so this gives you a practical way of finding almost optimal solutions for large systems of interacting agents. Okay, so what are the difficulties? Well, this is a system of coupled nonlinear PDE that has a forward-backward structure, which makes the analysis of these types of systems challenging. So, and as I mentioned, often these systems do not even have classical solutions, and you have to come up with the proper notion of weak solution. So you have to know how to appropriately relax the notion of the solution so that you have a good theory. So, and for more or less the same reason, it's also in a high-dimensional state space. So we could, of course, solve the problem of the number of agents, but the dimension of the state space didn't go anywhere. So we still have these problems. And if we're thinking about applications in engineering and economics and so on, there you typically have problems in high-dimensional states. So you can consider various modifications of these systems. You can say you can assume that the trajectories of agents are in fact noisy, and in that case you have to have these second-order terms in your equations. Or you can think that the trajectories of the agents are noisy, and in fact you also have a control variable in the noise term, in which case you get a fully nonlinear system, so there is also nonlinearity on the second-order derivatives, and so you get much more complicated objects. This is to say that there are many variations of these models. And also there's, I wrote here time-dependent models, you can have stationary models, and so on. Okay, so let me show you one application in machine learning. At this point, it's sort of mysterious. You know, we started from like looking at agents and so on, and now what does this have to do with any of the machine learning applications? Sentence explanation is that mathematically often we can look at data points as agents. This is a rough statement that you'll see that that's what's going on. And I'll be interested in one particular application, which is called normalizing flows. And let me try to sort of quickly explain what it is. So let's say that there is some unknown distribution, rho naught, and all we have from these unknown distributions are some IID samples that I denote by xi, I from 1 to n. And our goal is to come up with an approximation to this unknown distribution rho naught, and also being able to draw new samples from this unknown distribution rho naught. And these types of problems appear in machine learning when you are trying to do generative modeling. So you're trying to generate, I don't know, probably some of you have seen these recent progresses where these machine learning systems, they're able to produce high quality image, text, and so on and so forth. So sort of the underlying mathematical assumption is this first line here, that you have some samples drawn from unknown distribution rho naught, which is supposedly your distribution of images or, you know, handwritten digits or whatever, and you're trying to sample new ones, and you're trying to estimate the density. So there are various ways of, so you put an answer rho theta, so you where theta is some parameter, so you postulate a parametric approximation model rho theta, and you want to find theta star that maximizes the likelihood of this sample being drawn from row theta. So you want to maximize the product of row theta xi. Taking a logarithm, it reduces to the following minimization problem. Okay, so this is something that statisticians do all the time. They have various, statistical models for row theta. So could be, Gaussian, whatever. There are various choices. So one particular choice that I'm interested in is called, it's an ODE-based parametric model. So how does it work? So let's assume that you have a function v, which is called the velocity field. So it's a vector that depends on the position, time, and parameter theta. Okay, so this is a vector field that depends on the parameter theta. And what we do, we build this flow map. So z satisfies the equation z dot equals v t z, and you start at position x. Okay, so you start with some initial positions, then you drive your particles or your samples according to some velocity field. You stop at time t, and you assume that distribution that is known and it's easy to sample from. Okay, so we denote it by row 1. So essentially, what you want to do, you want to start from your initial row node or from your samples, and you want to drive these samples according to a suitably chosen velocity field v that depends on the parameter theta, so that you end up at normal distribution. So once you have this situation, let's say you're able to achieve this, it is easy to sample and calculate the density of the normal distribution. So you can generate new samples, and then you can run this ODE backward in time and obtain new samples from your row node. So this is the overall idea, and that's why these are called normalizing flows, because you start with row node, which is an arbitrary distribution, and then you drive your particles to match with some terminal distribution. Okay, so as a detour, a small detour. So why all of this has to do with the initial gains? Let's consider one particular example of initial gains where the dependence of the Lagrangian L on the density can be actually separated. Okay, so let's assume that Lagrangian can be written as some incisive Lagrangian plus something that depends on the density, and so we get this following initial gain system. So we do not need to go over them now, but under certain structural functions, essentially when you can integrate these nonlinearities in an appropriate sense, it turns out that this original system can be actually formally realized as the first solutions for the following infinite dimensional optimization problem. So in this case, these types under certain structural conditions, these initial gains could be seen as first order optimality conditions for some global energy. And for people who are familiar with also transportation theory, this is the extension of the celebrated Ben-Amu-Brenia formulation of the optimal transport problem. Okay, but in a nutshell, so this is the problem that you have, and I want to show, I want to make several remarks for the formulation here. So a quick question: until what time? So how much time do I have, Armen?
I think more or less like 10-15 minutes are fine.
Okay, that's great.
If you want to stay a little longer, that's fine too, but 10-15 is okay.
Okay, yeah, perfect. Yeah, 10 minutes is more than, yeah, okay, thank you very much. So let's examine a little bit this formulation. So you see that we're optimizing with respect to the velocity field. So once you choose V, it's velocity field, then rho is defined uniquely. So partial T rho plus the gradient of rho v equals to 0, right? So an optimal control problem, but now instead of controlling the position of a single agent, we're controlling the distribution rho. That's why I was saying that it's an infinite dimensional control problem. And there is a certain cost. It's very similar, right? It has some sort of a running cost plus a terminal cost. So we can think about this as an infinite dimensional optimal control problem. And again, the key thing is that we are controlling the distribution rho to achieve a certain goal. So how does it connect to normalizing flows? Well, it turns out that the mathematics of these potential mean-field games and the mathematics of the mathematical formulation of normalizing flows are in fact closely related. And so if we introduce this function, which is called a KL divergence, so mu and nu here are measures, so you can assume that, let's say, mu is absolutely continuous. We have to assume that mu is absolutely continuous with respect to mu. And let's consider this functional. And the properties, a key property that we're interested here is that for mu nu probability measures, this KL mu nu is always non-negative and 0 if and only if mu equals to nu. So somehow it measures the discrepancy of mu from mu. So the larger this KL, the further away our mu. If mu is from mu, the smaller the better. And so the normalizing flows problem can also be formulated in terms of a infinite dimensional control problem, where we control the density rho so that the KL divergence at the endpoint, okay? And our velocity terms here, they depend on this parameter theta. So we have our initial distribution rho naught, we choose this velocity field v for a given value of the parameter, we propagate it forward, and then we stop at time t, and we look at the KL divergence of the density at time t with respect to rho 1, and we're trying to minimize it. Ideally, if we can achieve 0 in the KL cost, then we're done, right? We found rho 1 exactly. Now, if we look at, again, at the potential mean-field gain formulation, you see there is a striking resemblance between the two. And what are the differences, right? So the differences are that, of course, in the mean-field gain problem, the velocity field is in a non-parametric form. So we're searching among all velocity field C. I mean, we need some kind of like regularity assumptions, but nevertheless, it's a non-parametric form. The normalizing flow is in a parametric form, so it assumes some postulates, some answers. Now, the normalizing flows do not have this rho L term, right? So this term is called a transportation cost. So somehow the normalizing flows, they lack this transportation cost. They only have a terminal cost. So summarizing, normalizing flows are an example of a degenerate mean-field gain, potential mean-field gain system where we only have a terminal cost. And let's see what does this lead to, right? So on the left, we have this image where in the bottom, it is our unknown distribution that could be far from the Gaussian, right? I think here it's probably mixed Gaussian, but anyway, it's far from Gaussian. And we have samples from this. I want to drive it to a target distribution, which is a nice Gaussian. So on the right side of the picture, we have the trajectories that are found using the normalizing flow technique. And you see that, okay, initially, so in this square with the curve, the bottom of the square is where our samples from unknown distribution are, and the top are the samples from the normal distribution. So you see that, okay, you know, these flows, they're able to drive the system from our unknown distribution to some known to the Gaussian, but the trajectories are very oscillatory, wiggly. On the left side, you have exactly the same problem, but now you add a transportation cost to your problem. And you can prove, so the optimal transportation theory tells you that the trajectories have to be straight line. And you see this in actually happening computationally. So the advantage of the left with respect to right is the following. So for all of this, and for at least for the original normalizing flows algorithm that people introduced, there is a black box ODE solver that solves these differential equations forward in time. And when you have this black box ODE solver, what it does at each step, it tries to make sure that the error is not too large, so that you do not deviate from the continuous trajectory. And when you have this wiggly and oscillatory trajectory that can go close to one another and so on, this ODE integration becomes harder and harder numerically. And at some point, the algorithm starts taking extremely small time steps, and it sort of like halts. It doesn't make any progress. Whereas if you have the straight lines, this problem goes away because the trajectories are more regular. And so, yeah, so mathematically, right? So the original problem was this, the top original formation is the top one, and in the bottom you add these two transportation costs that help you to straighten out the trajectories and obtain more regular trajectories. And in fact, adding this cost is not computationally too much expensive and can be done in a minimally invasive fashion. And yeah, so here I just show like one example. So in this table we report the convergence times for various algorithms, and the third line is still find the convergence, whereas the other one, the original ones, they do not have convergence for certain cases. And in some cases where you still have convergence, the time that our algorithm takes to converge is substantially smaller. And in the bottom, I show you three examples. So you have this real, it's called an MNIST data. Essentially, it's a data of handwritten digits, and you can model each of these handwritten digits as a vector in a very high dimensional space. And then you can, apply this algorithm and try to generate two ones. And then on the right side, where we have two images with digits. So the top one are the images generated by a standard normalizing flow algorithm, and the one in the bottom is generated by ours. So you can see that the quality of the digits is slightly better, but the important thing is that the convergence time reported in the table above are reduced. Okay, so maybe I'll take just a couple of minutes to wrap up with some considerations about the PDE aspect, and then we'll finish there. So from the PDE aspect, these problems are hard to analyze, and when I'm saying analyze, standard questions like exist of weak-solid pre-bounded problems and so on. And also, hand in hand, we have numerical methods, so efficiency and non-smooth. So you might have non-smooth solutions. So how do you make sure that you can recover those and come up with algorithms that converge? And especially these are interesting for first-order problems because there is no apparent smoothing mechanism here, like a Laplacian term or something like that. And in fact, there are examples, so we've shown that you can find examples where the density can vanish at some points. So these are the plots of the density for two various examples. So you see this flat part in the middle. These are parts where there are no agents. So it could happen that in equilibrium positions there are no agents in certain regions, and this makes the problem hard to study from regularity point of view, because in some sense, wherever there are no agents, there's no equation. So one has to make a precise sense of what the solutions mean. And one instance where these questions have satisfactory answers are the case of potential infield gains, because we can write them as first order. We have a variational formulation for them, so we can write them as first order optimality conditions for certain energy functionals. And so our goal is actually to come up to with the variational formulations for the potential initial gains, and so that we can come up with a analysis methods and methods to compute these things numerically, develop a regularity theory, solution theory, and so on. And I won't go into the details here, and I think I'll stop here. Thank you very much for the attention.
Thank you too. Let's thank our speaker for this gentle yet very thorough introduction to the topic. I'm wondering if there are any questions, please. So one thing I would ask, maybe it's a long shot, but is there anything like convexity there? Like, because in discrete Bellman equations, many times convexity helps kind of settle things and solve things, and the difficult thing is to find a Bellman function which is convex. What about this situation?
So for the, let's see. Yeah, so if we go back to this potential initial gains formulation. So, yeah, so if you have a variational formulation, you want to essentially, so when are the variational formulations most useful? When you have some sort of convexity. The problem here, there's a trick that you can do, which is you can introduce a new variable, rho times v. So the flux, you can pass to the flux density flux variable, and that makes the constraint here linear and the cost function here convex. And once you have this situation, you can prove existence of minimizers, you can prove regularity of minimizers, and you can do various things with it. So if we think about just the Hamilton-Jacobi equation, so for example, this one here, so you could also consider Hamilton. So we came from the optimal control problem, but you could also consider Hamilton-Jacobi equations on their own. To say you have some Hamiltonian function and so on. Now, for problems that are coming from control, this Hamiltonian function h is actually convex in the gradient variable, and it helps a lot. So you can study, of course, more general Hamiltonians that are non-convex in the gradient variable, but still they have some growth conditions and so on. But the analysis there is difficult because you do not have this variational principle coming from control, and the proofs there are more involved. But still, it's possible to do. So yes, in general, you want to take advantage of convexity if possible and find convex structures, or if you can't find monotone or something like monotone mappings or something like that.
I wonder if there are any more questions relating to Levon's talk.
Yes, I would like to ask a question. And first of all, thank you very much for a presentation. So regarding my question, maybe two questions. They are regarding to these normalizing flows. And you made the analogy of generative modeling, etc. And usually in this generative modeling, you don't want to repeat the images or whatever objects you are observing. And so hence my question is, do you have any guarantees that the distribution that you are sampling from in the end, it will not repeat the previous observations? Or do you have some other guarantees how close this distribution is to the true one, to the unknown row zero distribution?
Yeah. So no, we didn't study.
Okay.
We didn't perform any theoretical analysis in that direction, neither an empirical one. But if you're interested in such questions, then if you look at this formulation, then there is almost no. Okay, I wouldn't make that that bold of a state. Come up estimates of how close you'll be to your terminal condition if you do not have any regularity mechanism. So in this formulation, you would probably be able to prove something like that, but we didn't do that. So there is something else that you can in fact do. Let me see if I have it here. Yeah. So in fact, here is what's going on, right? So once you choose these positive constants, lambda k and lambda j, then of course there is no way you can find, let's say you can perfectly find that, even if you're in a non-parametric regime, there is no way you can perfectly make this zero, right? And so it depends on this, if these are positive, there is no way you can make this zero. So, and this is a typical situation that occurs, people have known this occurring in problems like inverse problems or denoising problems and things like that. And one workaround to improve the accuracy here and to make sure that you can recover at least in the non-parametric regime, because there are two different things, right? So the non-parametric regime and then how your parametric model approximates your non-parametric regime. So the non-parametric regime, what you can do, you can solve a sequence of problems like this where you start with your own solve this problem, and then you come up with some terminal condition row. And then you take that terminal condition row and then solve the problem again, now thinking about it as your initial condition, and so on. And you can prove that, so if in the case where lambda j is 0, this is definitely, you can prove that. So then you can prove that this process corresponds to a backward discretization of the gradient flow of the scale divergence, and you can in the suitable space, and you can prove that the gradient flow in fact converges to row 1. So this procedure of solving the problem repeatedly, it guarantees that you can converge to the solution, and we've done this in our latest paper. If you're interested in that, I can later send it to you. But this is something that people know how to do in like optimization, inverse problems, and things like that. And of course, the second question is how the parameter non-parameter regime approximation works, and that's a different problem, and of course it depends on the structure of your approximations and so on. But we didn't do this analysis in the paper, and also we didn't analyze the non-repeating aspect.
Okay. Way to choose them, and does a lot depend on the choice of these parameters, or not so much?
Yeah, that's a very good question. So if you're solving this problem in a sort of one shot, like here, then there is dependence, of course, on these parameters, and so you want to strike a balance between, you know, like optimizing this part and this part, and typically this is done by a grid search, right? So you do like empirically, you try various lambda k's, and you try to go over different like magnitudes. But it wasn't too hard to sort of come up with reasonable ones. And in the paper you can see more details about that. But the second approach, another advantage of the second approach of solving this repeatedly is that in the non-parametric regime, this algorithm will converge to row one for all positive constants, lambda. So this means that you do not need to tune this hyperparameter. You can choose, you can choose it almost arbitrarily, and then you can see that across the board you get similar results. Of course, one shot is computationally more efficient, but until you find your best lambda, you might have done many iterations, right? Whereas there, it's like, okay, and you can automate this process, right? You can introduce a certain tolerance or whatever, a certain measure of success, and say, okay, do as much iterations as you need until you reach this and you stop. And so, yeah. But yeah, that's a good question. Yeah.
Yeah, it's clear. And there is some kind of trade-off of how much computation you want to put in, and then for what values of lambda it will converge. Okay, I see. Thanks.
Yeah. Thank you for the question.
I wonder if there are any more questions. If there are not, let me use the chance to tell you that we will hear Levon again on Saturday, April the 8th. And also, since Lagrangians were mentioned in between, on Saturday, March 25th, we will hear Karapet Mukherjee from Imperial College London, who is working in physics. So this will be our attempt to link somehow physics to mathematics. So I'll be waiting you all for these upcoming two talks. And also, let's thank Levon again for his talk. Thank you so much.
Thank you very much. Thank you very much for the invitation.